Okay, so here we go. We're going to jump right into 13.5, and this is going to be short. And the reason it's short is not because it's not important, but we don't have a ton of time left, and it's very, very algebra intensive. Just a lot of computations. In fact, most of the time it's done with a computer. But the topic is this thing called the TNB frame. And there's another name for that. It's also called the Frenet. That's French. It's pronounced Frenet Frame. And it's a special kind of a coordinate system. And the way it works is like this. Let's say we've got some particle that's moving at us in such a way that its unit tangent vector looks like this. Okay, so we're going to say this is the unit tangent vector. So it's moving in this direction. That's all we know about it. And then I'm also going to say that it's got some unit normal vector that looks like this. Okay, so now what can we tell just from this much so far? Well, if the tangent vector is going like this and the normal vector is going like that, it must mean then that the particle's path is doing something like this. Okay? It's got to be curving this way because the normal vector always points towards the center of the osculating circle. So if we had an osculating circle here, the normal vector points towards the center of that. The tangent is going this way. Now we've talked the other day about a potential third unit vector, and we're going to define that as B, which equals t cross n. So I can't draw my right hand here, but if we did a right hand rule, if we curled from t to n like this, that would leave us with some other normal vector or unit vector that looks like this, which we call b, and then so this is set up so that all these are right angles like this. So we've got three orthogonal unit vectors here. And so since t and n, the magnitudes of both these are 1, the angle between them is 90, that means the magnitude of b, the magnitude of this thing, must also equal 1. Okay, now we know that t, n, and b, right, it's either there are three orthogonal unit vectors to make a convenient coordinate system. Much like I, J, and K. Much like, let's rewrite that. Much like I, J, and K. Except that I, J, and K are always kind of pointing in the same direction. They're fixed with the coordinate system. T and B can be anywhere and point in any direction relative to the particle. So we can use this fact. Oh, by the way, B stands for binormal. Okay, so it's the binormal vector. We can use the fact that that T and B make this coordinate system to break up the acceleration vector, break the acceleration vector into components. And so we'll look at the acceleration vector. So instead of breaking it into I, J, and K, we're going to say it becomes A sub n times, or no, that's not right either. We're going to say that's, start with tangential because T, N, and B go in that order. So it's got some tangential velocity, or a tangential acceleration times the magnitude times the tangential normal vector. So this is a scalar, this is a vector, this is the magnitude, this is the direction, plus some normal acceleration times the normal unit vector, and you might guess that it also has some binormal component times this binormal unit vector. All right, now we've talked about this, the tangential acceleration, which is the kind of the change in the speed, and we've talked about the normal acceleration briefly in class. That says how is the tangent changing, right? Because remember that the normal vector can also be defined as the tangent vector with respect to the arc length parameter dTds. So since this is a unit vector, only its direction can change, and so normal vector is kind of what's the normal acceleration is what's causing the tangential acceleration to change, right? So let's look at this third one here. What does this binormal component of acceleration really mean in a physical sense? Let's take a look. So we've got this kind of cool demo here. And the graphics aren't working out well because my student license for Mathematica has not yet, or has expired, since I'm no longer a student. And I don't have $1,000 to spend on the real version, so I've just got to use this demo. So what this is a 3D box, and it's got this helix kind of going up in it. And we have these three vectors here. Okay, so let's look at it from the top down, like this. So we've got a green vector here, we've got an orange vector and a purple vector, and hopefully you guys can see this okay. So green, orange, and purple. Now, you may look over to the left, but the green one seems to be tangent. Okay, the green one seems to be tangent to the particle's path, which means that's probably t, the unit tangent vector. The orange one, the orange and purple are both normal to that, but if we look from the top down, the orange one seems to be normal to the green one, but pointing towards the center of what might be the osculating circle, right? So we're going to say that the orange one is the unit normal vector, which leaves the purple one to be nothing but, oh, here it is, the binormal. Now you see this error message coming up all the time. That's because I can't access the code to this thing, and I can't fix whatever problems are in there, nor write my own, so here we are stuck. All right, so we have a good sense for the green vector here, right? That's the tangent vector, unit tangent vector. And if this particle were accelerating, like its speed were increasing, if the speed were increasing, the magnitude of that acceleration would go along this vector here. And since its direction is always changing, since this thing is like a helix, it's always accelerating towards the center of some circle, and that is what that orange vector does. But what does the purple vector do? Well, let's slide this thing along back and forth here a little bit. So I can slide this, and notice how the green one is always parallel to the path. The purple one, or the orange one, is always pointing towards the center of the curvature. And the purple one is always kind of pointing off into space. Well, as it turns out, there can be no acceleration in the purple direction. Why can there be no acceleration that way? If it were accelerating in the purple direction, it would be changing the direction of the unit tangent vector. If we change the direction of this, then that changes this. So really, this can't be changing. This almost has to be constant, at least it can't be accelerating in that direction. And this is really hard to explain without using my fingers and kind of pointing in various directions. But you can see that the green one is kind of a function of the path, and the orange one is a function of the curvature. And if we had some acceleration in the purple direction, it would change all the other ones, so we wouldn't really have that same coordinate system. All right, so let's go back to here. We can say that since we can't have acceleration in the b direction, We can't have any acceleration that way. So the acceleration vector can be broken into just two components, always just two components, even in 3 dimensions. And that is AT times the unit tangent vector plus AN times the unit normal vector. So what does this really mean here if we, I think I've got a picture of it over here, if we've got a particle traveling along some path, let's say it's kind of going like this, and its speed is increasing, or it's got some acceleration. I'll draw this one here. This is, so if it's actually speeding up, like the magnitude of velocity is increasing, that would be this, AT times the tangent vector. If it's also heading into the, the curvature is changing somehow, so it's accelerating this way, we could call this as AN times the normal vector, right? Because the tangent vector goes in this direction, so the acceleration, tangential acceleration, just scales that. The normal unit vector points in this direction, so AN, the normal acceleration, just scales this vector to get these two. Well, that equals, if we take those two vectors and add them together, that gives us this third vector, which is a parallelogram like this. In fact, it's not even a parallelogram, it's a rectangle, isn't it? Because these two are normal. If this makes a rectangle, then this must be the same as this. So we can say that, and I'll try to do this color-coded. What color am I now? I'm in green. So we could say that, well, this is the original A vector, that the magnitude of the acceleration squared will equal the tangential acceleration squared, but the tangential acceleration really is the magnitude, the derivative of the velocity with respect to time squared plus, and then we've got the orange component, A sub n squared. Well, this just looks like a mess. Why does this help us? Because we can easily find the acceleration vector as the second derivative of position. So I can rewrite that as d squared r vector dt squared. I'm going to take the magnitude of that. So that is a fairly easy calculation to get. I can easily do the second one here. I mean, this is easy enough to do. I can take the derivative, find the magnitude. Well, what is this? This is d times d of, or the differential of, the first derivative of the position vector, with the magnitude of that. So I find the derivative of position. I take the magnitude to get the speed, and I see how is the speed changing, and that really is the tangential component. And then I square that. Oop, I forgot to square this first one. And then I have to square the second one. Now, while these are cumbersome to do, they're very doable. It just becomes an algebra fest. And finally, I've got plus my normal component of acceleration squared. So my normal component of acceleration, which would be pretty hard to get, would be doable by the square root of the difference between these two. So that's doable. Clearly, this becomes an algebra fest. As such, I'm not going to assign any homework. We're too close to the end of the semester. The cross product is doable. In fact, I've assigned a couple of those to do, but you can do those by hand easily. The what's called the torsion and finding these components of velocity. It's just a bunch of busy work, and I'll do a little demo tomorrow if you want. But you should be aware of it. You should be aware of this moving reference frame, but we're not going to do a bunch of algebra with it. So that is it. That is the end of the new material for the semester. I look forward to the next week of review, and we'll talk soon.